Okay, so here's our second video of this topic set, and we're going to start to look at momentum and impulse in kind of a detailed fashion. Last video was our introduction video, so we just kind of did a brief overview looking at it, and we did talk about momentum being kind of this quantity of motion. So I gave, this is about as good a definition as I could come up with for the way to kind of talk about momentum. The quantity of motion in with which a body proceeds in a certain direction. Now this is kind of a key indication here. Whenever you see this in a certain direction, we're starting to understand that momentum really is a vector quantity. It's not a scalar quantity like energy is. Momentum is a vector quantity, very similar to like a force. So typically we know that velocity is a vector quantity. And when we take mass times velocity, we get momentum, and that makes momentum a vector quantity. And I probably should back up here and explain a little bit here. The P here stands for momentum. Kind of because of the whole proceeds thing, it was one of those historical pieces that went through and said, you know, I'm going to start labeling momentum with a P because it's the way that it kind of proceeds, or it's a part of it. Okay. And so that's why the P ended up getting used. So P stands for momentum. And again, momentum has a relationship between the mass of an object and the velocity. Now, again, when we always look at these things, we like to start to examine what do the units look like. Mass is in kilograms, and velocity is in meters per second. So we're looking at a kilogram meter per second. And that's really the way that we kind of talk about momentum, is in kilogram meters per second. As far as it goes, we can always look at how much momentum we have. Okay, so if I have big momentum, I have one of two things that's actually happening. Either I have a very big mass, or I have a big mass small velocity. Okay, or I could have a small mass with a big velocity. Okay, and so really it's about the relationship that we see between these variables. Okay, so if two objects maybe have the same momentum, one could have a really big mass with a very small velocity, and the other one could have a really small mass with a really big velocity. When we look at these relationships, for those of you that remember my little triangle stuff, momentum then is a mass, a velocity, and a momentum. Again, that's kind of the way we described it in 9th grade science, so you could just cover up one of those three corners and you'd figure out the others. You guys are so good at your algebra skills right now. Looking at it from this standpoint is good. Again, when we started to look at how momentum kind of set up, Newton really wanted to look at this from the standpoint of his second law. And so we kind of look at it from that point of view. Let's see, what else do I want to talk about before we leave this. Go to the next slide here. So how's this whole impulse thing fit in? Well, it's called the impulse momentum theorem. Okay, and really it goes back to the way that Newton first wanted to talk about his second law of motion. You remember the second law of motion is Fermat. Okay, so in other words, a force is equal to a mass times an acceleration. But really, acceleration is nothing more than a change in your velocities over a change in time. Okay, so we started to look at it from that sense. When you rearrange this, you actually get this. Now what Newton wanted to do is he wanted to call this side of the equation, this force times a change in time, the impulse. Okay, and so in other words, if a force is acted upon some object and it has a certain amount of time that it's acting upon it, we create this thing called impulse. And that impulse is what actually changes the momentum of an object. So in other words, I have an object like a car driving down a road, and it's heading there at 55 miles an hour, so it has a velocity, and the mass of the car is constant, and all of a sudden the car hits a wall. Okay, so in other words, we now have the amount of time that it's impacted, and we can look at the force of that impact based upon the amount of time in contact. Now this is a big thing for our car companies. The picture that I chose here was of one that they were studying a momentum situation, so we were actually looking at a collision, and they want to increase this time. So if we can increase the time, then we can change the amount of momentum that we have. Okay, and so this is the reason why when we now currently design a car, we design a car with the idea of having crumple zones. Okay, and so what a crumple zone does is that it takes that force, that amount of force that we're using, and allows that force to expand through the amount of time. So it allows us to change our momentum at a slower rate than what we normally would. Airbags, okay, are another thing that we use to adjust the amount of momentum, okay, or change our impulse. So again, we're back to that force, and if we can apply that force over a longer period of time, it allows us to look at our momentum in a much different fashion. Okay. All right. I did put this down here because I like to look at graphs. So if we look at the graph of force versus time, if we have, say, a constant force and it acts for a certain amount of time, we get kind of this rectangle feature where F is related to T. Excuse me. F is related to T. And we can then say, well, that looks like an area thing. Okay? So it kind of goes back to the way that we first talked about work. If we take force times time, that's an area. Okay? And so the area under that curve is the momentum when we look at a force versus time graph. Okay, so again, it's another way that we can kind of look at it. Impulse, again, big topic. It's a big equation, but really it's nothing more than what we've already learned, which was Newton's second law. Let's see. So let's look at some examples of where we see this momentum stuff. Okay, or at least the impulse stuff. So I picked a couple of different sports pictures because, again, that was one of the things that I talked about in the introduction video. Momentum is one of those things that we see all the time in our various sports, and it's about contact time and the amount of force that we can put to change the momentum of our whatever it is that we're trying to hit. If we kind of work in this fashion here, this is probably my favorite one right here because I'm kind of the golfer. You can see the ball is actually being deformed or flattened out. Okay, which is kind of an interesting thing. But again, because it's deformed and it's flattening out, we create an amount of time that golf head club is in contact with the ball. So again, it's about the time in contact and the force that we're applying, which means that we're going to then see our momentum change. Okay, so the club head comes down, it has mass and it has velocity. Okay, the force is impacted on here, so we have the change in time. Now we have the change in the momentum. So some of the momentum is going to leave the club head and go into the ball, and the ball's momentum will change as well. And that's kind of how we look at it. But again, it gets back to that time in contact. Here we have our baseball player. You can see that they've got the bat, and even the ball is kind of wrapping itself around or deflecting around the bat. Okay, and so that's creating that longer contact time. So if you can apply the force for a longer contact time, you're going to have a bigger change in your momentum there. Okay, and so we can look at that and we can try to take that and extend that out. So that's where we see the ball in contact with it. So again, original momentum of the ball was in this direction. The returning momentum is going to go back in the opposite direction. Here I like this picture too, this tennis player. We've got the ball that's actually seen, and so again, the racket itself is changing and deforming, so we get this deformation of the strings in the racket. So it's actually absorbing some of that energy, and then it's going to return that energy back, and it's absorbing that momentum, and it's going to return that momentum back. Again, looking at that force in contact with the amount of time. The longer we can keep that force in contact with the time, the better we are for our momentum in our sports. Last picture here, we have our hockey player, and now this is the big thing in hockey, because I'm from northern Minnesota, where we played, we went out and skated for recess. That was our recess up there, and so you had a lot to do with hockey, and a lot of the older sticks were all straight wood sticks. Okay, Christian Brothers was our #1 stick manufacturer here in Minnesota. And now all of a sudden we've gone into these whole composite hockey sticks. And so you can see that the hockey stick itself is bending, which allows us to kind of spring load how much energy we can put into it. So you can start to look at that whole potential energy of a spring. And then we are going to keep our stick in contact with the puck for as long as we can, so we get the bigger change in momentum. Okay? Bigger the impulse, the bigger the change in momentum. And that's going to be the kind of key thing. So we like to look at that in terms of our sports. Alright, last thing I've got here on our video is an example problem. So here we have our car, and it's going to have a big change in momentum because it seems to have run into a light pole. So again, we know the mass of our car is moving westward. It has a velocity, collides with the utility pole, and is brought to rest in that much time. So now we're looking for the force. Okay? So again, force times time, that's our impulse, is equal to the mass times the velocity, okay, or the change in our mass and the change in our velocity. But when it's brought to rest, that means that our I should write this out this way. Our force times velocity is equal to the momentum mass velocity final minus mass velocity initial. There's our change in momentum, okay? But our final velocity is 0, so in other words, that's going to be thrown out of there, okay? When we look at this, our force was what we're trying to get. Our amount of time that we're going to be in contact is 0.30 seconds, okay? And then when we look at this, our momentum is 1,400 kilograms times 15 meters per second, and that's a negative value. So I'm just going to grab my calculator. 1,400 times 15 gives me 21,000 kilograms meters per second. Now when I take this force times the 0.030 seconds, I divide by 0.30 seconds. My force now is equal to divided by 0.3 70,000 newtons. Okay, and again, it's newtons because it's kilograms meters per second squared. Okay, which is a huge amount of force. Okay, that's a huge amount of force of when we're actually hitting this. And the way that we decrease the amount of force is by, again, changing our impact time. So if we can change our impact time, if we can make this bigger, it makes the force smaller. Okay? Which is why we want to have those crumple zones and why we want to have airbags, so that we can decrease that amount of force of impact for us. Okay? So there you go. That's kind of our how we deal with this and this momentum impulse theorem. And if you have any questions, feel free to post on the doc, and we'll see you in class tomorrow.